missing?
Let's see. Give me a minute to.
Yeah, no worries.
Any questions about anything? So there's a question about the defining function for a curve, and the gradient being non-zero means it's a. So what's the question about the gradient being non-zero?
I probably need to actually figure out what I meant by my question in my head.
Okay, we can talk about that later. It's kind of the inverse function theorem that if the gradient is non-zero, then you could express that that row as a graph. It's kind of equivalent to that, but you don't have to express it as a graph. I gave it to you in the easiest form to deal with, but it will be important to know that the gradient of that defining function for the curve is not zero in that problem about mapping an open set into a curve, which is too small to be anything except a constant function, if it's analytic. We can talk more about it after class. Any other questions about anything? Let's see, I wanted to get something out of the way today that I've been telling you, but I kind of thought you'd read it in the book, but I thought I'd do it today. Today I'm going to show that analytic functions are given by convergent power series. That's another one of the biggies, and rather surprising, very special property of analytic functions. It's way false in the real domain. So being one-time differentiable in a real function, it's possible to not even being twice differentiable. And so definitely not equal to a power series. Anyway, we know today, after getting the Cauchy, higher order Cauchy formulas and realizing you can differentiate them again and again, that if f is analytic, then f prime is analytic. And of course, therefore, f double prime is analytic. And if f double prime is analytic, that means that f prime is differentiable and is therefore continuous. So we know that all those derivatives are continuous. So it's infinitely complex differentiable. Every derivative is continuous. And if you write red box number 1 and red box number 2, remember that if a function is continuous, then the real and imaginary parts are also continuous. So red nut box number 1 would imply that du dx and dv dx are continuous, and red box number 2 would imply du dy and dv dy are continuous. So we know that all the first partials of u and v are continuous now. And of course you can repeat this again and again. You'd get red box number 1, 2, 3, and 4 when you differentiate again. And that would allow you to see all the second partial derivatives of u and v are continuous. And then, of course, you get twice as many the next time you do it. But every time you do it, you get all the partials. Some of them are redundant because the mixed partials are all going to be equal. So you get lots of boxes, but many of them are redundant. Doesn't matter what order you differentiate in, provided the next derivative is continuous. And, of course, it will be. Anyway, it's not hard to convince yourself that all the partials of u and v exist and are continuous when f is analytic. So that means they're C infinity smooth. And what I wanted to show you, something I kind of skipped earlier, is that means u and v are harmonic. It's a really elementary thing to see. Harmonic means the Laplacian d2u dx squared plus d2u dy squared is 0. Same for v. Anyway, you write out the Cauchy-Riemann equations there. And let's see, I'll call them a and b. If I differentiate a with respect to x, I'm thinking I want to get du dx dx. So I'm going to differentiate a with respect to x. And then I'm thinking I'm going to differentiate b with respect to y. So I get du dy dy. Okay, because those are the pieces of the Laplace operator. Okay, so there's the result of doing d by dx on a and d by dy on b. And because it's important to know here that v is C2 smooth. That's important here. And that means these mixed partials are equal. Okay, and so that means du dx x is equal to minus du dy dy. So yeah, I'm using that key fact right here. I needed to. That's the reason I couldn't do this on way back. First of all, I didn't even know that I could calculate those second partials. I didn't know they existed. And I didn't know they were C2 smooth, so I could use the fact from sophomore calculus that when something's C2 smooth, the mixed partials are equal. Okay, that's why I needed that today. And similarly, to do the Laplacian with respect to V, I'd take du by dy of A and d by dx of B and play the same game. So it's harmonic too. Questions about that? That's a great thing to know. Harmonic functions are just as special as analytic. In fact, they're kind of equivalent to being analytic from the point of view of, from several points of view. Let's see. So today I'm going to do this thing. I need this big fact. I need some recall some notation I set up, because it's still true that if you understand the geometric series, you understand all power series. And in this case, if you understand the geometric series and the Cauchy integral formula, that's all there's going to be to this fact I'm going to show you. Okay, so there's the classic formula for the sum of a geometric series with the error term. All right, I'm defining those terms there. I called that nth error term En of z previously. Maybe it was plus or minus that. Anyway, this is what I'm going to call it today. And we did the basic denominator estimate, and we're able to show that if mod z is less than rho is less than 1, then that error term is, in modulus, less than rho to the n plus 1 over 1 minus rho. Okay. So that's the notation I'll use today. And the big theorem is that if f is analytic on a disk of radius r about z naught, then f is given by a convergent power series in that disk, where the an is given by Taylor's formula. And the radius of convergence of that power series is guaranteed to be bigger than or equal to r. So in the picture there, if I know f is analytic on an open set, and I pick a point z naught, the biggest disk I can squeeze in there, could apply this theorem and see that the radius of convergence of the series there is bigger than or equal to the distance to the boundary on the set where f is known to be analytic. Of course, if f was a polynomial, that radius could be infinite. But if it had a singularity on the boundary there, well, then it probably is less than or equal to R2. We'll see that, an example of that in a second. Well, the proof of this is going to be a snap. It's just a matter of writing out the Cauchy integral formula and looking at it. So the proof of the theorem is, let's see, I want to simplify things a little bit. I can assume that the center point is the origin, just to make, so I don't have to write z minus z naught all the time. And we're going to do the usual trick when we're dealing with power series. I'm going to let 0 be less than rho, less than r, less than capital R. And of course I can squeeze those out, rho and little r, as close as I want to big R. And of course I'll do that at the end. And now I'm going to, here's going to be the big disk of radius capital R. Then I'm going to shrink it to a smaller disk. And this is the one the green one is the one I'm going to integrate over. That'll be C sub R. And let's see, I'm not taking z naught here, I'm taking the origin. And then I'm going to assume that my z that I'm going to put in the power series here is contained in a smaller disk of radius rho. Okay. So the various radii here are little r, and then this is the big circle, capital R. So it's analytic on the big circle. And then I'm going to apply the Cauchy integral formula and write that f of z, let's see, z is inside here, inside the smallest circle. And f of z by the Cauchy integral formula is 1 over 2 pi I integral around the green circle, going counterclockwise, of f of w over w minus z dw. Okay, and the w there in that integral is over here. And I want to think of geometric series. Geometric series they converge when the thing is less than 1 in modulus. And you can think of how I would get something less than 1. Mod z is less than mod w. So z over w is less than 1 in modulus. So the brilliant thing to do here, if I'm thinking about geometric series, is to, let's see, I'm going to pull out the w. And so I'll have f of w over w here. And then I'll have a 1 over 1 minus z over w. And the reason I chose w instead of z is I need that to be less than 1. When I do Laurent expansions, I'm going to choose z when I do the negative powers of z parts when I do this. Anyway, we'll do it again later when we do Laurent series. Today's power series, and that's where I divide by the w. I pulled it out there. And now I'm going to use that form. I'm going to use my notation I set up. This is going to be a Sn of z over w plus the En error term. Okay. And when I do the Sn term, that's where the power series is going to come from. So this is going to be 1 over 2 pi I. I'm going to interchange the sum with the, let's see, yeah, f of w over w stays, but then I would get here 1 plus z over w. This is where the power series is going to come from. Z acts like a constant in this thing, so I can pull it out. dw. Okay. And the rest of the junk is going to be 1 over 2 pi I integral around c sub r f of z over w f of w over w times the nth error term here dw. I'm going to call this, notice it's a function of z because the w integrates out. I'm going to call this curly e sub n of z. I'll estimate that and show that it gets small, uniformly of small, in fact. And this is the stuff that's going to spit out a power series. Let's see. When I write it out, this is going to be the sum. The powers of z go from 0 to capital N. And I can pull out those powers of z because they act like constants. Then what's left inside is, let's see, we'll have an f of w. I get a w to the n from the stuff inside the square brackets, but then I get a w out in front. That gives me a w to the n plus 1. And that should look familiar. That's the higher order Cauchy formula at z naught equals 0. So this thing right here we recognize as the higher order Cauchy. This is equal to, let's see, there's missing the n factorial in front. So in fact, it's the nth derivative of f at 0, and the n factorial is missing out in front, so that it's actually that divided by n factorial. That's the higher order Cauchy formula. Okay, and so that was the power series I was expecting. The last thing I have to do is estimate that error there to show that it goes to 0. Take a look at that error. Let's see, I'm just going to do the basic estimate now to estimate that error. Maybe I should do it up here where we can see it. Let's see. En of z going to be less than or equal to 1 over 2 pi. The max of the f, let's call that m. That's the max of f of w on the circle. Okay, and I got a 1 over w. The modulus of w is r on that circle. And then I use my estimate for the en of z function. And the en of z, it's en of z over w. Okay, and z over w is less than modulus rho over r. So this is going to be a rho over r to the n plus 1 over 1 minus rho over r. Because mod z, the modulus of z over w, z is less than rho, and w is equal to r in modulus. So that modulus would be less than rho over r. Okay, so that's my estimate there. And then finally, I need the length of the curve, which is 2 pi r. And the fascinating thing is that goes to 0. So let's see, I should say where m is equal to the max of the modulus of f on c sub r. And the great news is that en of z tends to 0 uniformly. When mod z is less than rho is less than r. And that's less than capital R. So the power series converges as promised. And because it converges on that disk, we know the radius of convergence is at least r. Let's see, finally, I can squeeze rho r out to capital R to see that the radius, see the power series convergence on the disk of radius capital R, about in this case 0. And so that means that the right radius of convergence is greater than or equal to r. Okay? So let's see. Today, for example, we know that the exponential function is analytic. We checked that by Cauchy-Riemann equations. And therefore, we can write the power series for the exponential, and it's the famous thing you expect to get. And here's an exciting fact. Questions so far? That's the big one for today. But now I've got a couple small ones to think about. Here's a corollary. We can differentiate power series again, and again. And what we get, the fact is, the radius of convergence of the power series for F. Okay, let me see. We know we can differentiate power series. We proved that last time. That was a Moreira theorem proof. So let's suppose F is analytic on dr z naught, where r is the radius of convergence. Then, of course, we know that F prime is analytic on the same thing. And I claim that the radius of convergence of F prime is the same as the radius of convergence of the series for F. That's the thing I'm trying to say here. And the proof is going to be elementary. The order I do this in makes this kind of a weird moment because we have to think about it more than I could use. Yeah. Typical books might say, oh, it's just Hadamard's formula. I kind of like to avoid that because then you have to think about limb soups and facts about limb soups. You can understand this without doing that. So, we know that F prime is analytic on the same thing. And I want to see that the radius of convergence, so F prime analytic on that disk, we know that implies that the radius of convergence is greater than or equal to that R. Let's call this R sub F. Okay, and now you got to think about, well, what the heck? What if it was bigger? That would be weird, wouldn't it? Because that would kind of mean that F prime is analytic on a bigger set. And you would think that, that would mean that F would have to be analytic on the same bigger set. And that's exactly the right way to think about this. So my claim is the radius of convergence of F prime is less than or equal to the radius of convergence of F2. So they're equal. Okay, so why? Suppose the power series for F prime converges on a bigger disk. A bigger disk. Let's call it D sub R about Z naught, where R is bigger than the radius of convergence for F. Okay, then we know it converges to an analytic function. And let's call that analytic function, let's see, that converges to something analytic on that bigger disk. Converges to, let's call it script F. which would be analytic on that bigger disk. Okay, and we know we can cook up antiderivatives because that's a convex set. Cook up f, which is an analytic antiderivative of that script f. On the convex disk. So we'd have f prime equals that script f. Okay, well, this is an antiderivative of f prime, so of course we expect it to be the same as f. Then we have d by dz of f minus this capital F antiderivative. That's equal to f prime minus f prime. That's 0. Let's see, that's equal to 0 on the set where it's analytic. That's the smaller set. That would be the radius of convergence of f about z naught. So that means that it's equal to a constant. On that smaller disk. But here's the funny thing now. If I write f, little f, is equal to f plus c, the power series for the thing on the right has a radius to convergence that's strictly bigger than the one on the left. But they're the same functions. R of c is greater or equal to my r. And here, the R of c is less than r. And that's the contradiction. So that f prime couldn't be converged to an analytic function on a bigger disk. And maybe I've overkilled that again, but I guess if I was doing this in a smart way, I should have proved this this next thing before I did that. Power series are unique. Uniquely determined by Taylor's formula. I'm doing this in a different order than some books, and so I'm going to have a different proof than you see in most books of this fact.
I have a quick question.
Yeah.
So we had f minus big F is c on that specific radius. How can we then write f as f plus c?
On the disk, that's true on the smaller disk. I don't know, and the radius of convergence is determined by the function in the neighborhood of z naught. Means those power series are only determined. Yeah, let's see. So I really should have done this next fact first. They're uniquely determined. They would have the same power series, and one of them has radius of convergence less than r, and the other one has radius of convergence bigger than or equal to r.
Okay, so we're basically inherently creating the power.
Right, that's where the contradiction comes from. Those are going to be the same power series. They have to agree on the smaller disk, and so that makes them the same, period. This should have been a lemma. So Sorry, I should have done this first. Then the thing I just did would make a whole lot more sense. Sorry about that, but I'll do it now. It's easy. So let's see. So the proof is easy. Proof. Suppose I've got f given by a power series. And let's suppose it converges. Converges uniformly on a subdisk. Then I can write, and why don't I take 0 less than rho less than r less than capital R like I always do. Then I can write the nth derivative of f at 0 is given by the higher order Cauchy theorem. Let's do C sub rho. And I have f of z over z to the n plus 1 dz. But f is given by a convergent power series, so this is n factorial over 2 pi I integral around c sub rho of 1 over z to the n plus 1, and f is given by sum as n goes from 0 to infinity an. Oh darn. Let me take my z naught to be 0. Okay, then this would be an z to the n. And because this converges uniformly, I can interchange the integral with the sum. I demonstrated that last time when I was using Morera's theorem. And so here I would get n factorial over 2 pi I, and here I would get a sum as n goes from 0 to infinity of an integral of z, of the an would come out, and I would get z to the n minus n plus 1 dz. And that's usually 0. Those are usually the derivatives of something. Okay, so the deal is these are all 0 except when that coefficient, these are all going to be 0 except, because they're derivatives of something, except when n minus n plus 1 equals minus 1. That's stupid. This is n minus 1. That's going to make this make sense. And so that's exactly when n is equal to little n. Big N is equal to little n. And so this is going to spit out, that spits out 2 pi I. And so this is going to spit out n factorial over 2 pi I a sub n. And then that integral is going to be the integral of z to the minus 1 dz. And we know that that's 1 over z is 2 pi I when you integrate it around a circle. And so that's what you're expecting. We see that the coefficient an has to be given by Taylor's formula. Questions about that? Okay, so now that previous argument makes more sense because those two functions agreeing on a disk would have the same Taylor coefficients. And one can't have a different radius of convergence than the other. Okay. By the way, this also shows that you can differentiate power series term by term. Inside the radius of convergence. I mean, if the radius of convergence is positive. Why is that? Let's see. Oops. Let's write it like this. So f prime would be the sum as n goes from 0 to infinity of bn z minus z naught to the n, where bn would be f prime nth derivative at z naught divided by n factorial. And that would be equal to f to the n plus first derivative divided by z naught over n factorial, and now I'm going to give myself, I'm going to divide and subtract by n plus 1. Then I get the a-nth coefficient. That would be the nth plus first derivative at z naught divided by n plus 1 factorial times n plus 1. In other words, bn is equal to n plus 1 an plus 1. Which means that's what you get when you differentiate that series term by term and write out the series in terms of an. Okay, let's see. Okay, those are the biggies for today. Next time, we're going to talk about the zeros of analytic functions. And I'm going to show you that the zeros of analytic functions behave a lot like polynomials. So zeros of analytic functions are like power series, and power series are like polynomials. They behave like zeros of polynomials, and you can sort of factor them out. And to motivate this, here's the y. If f is not identically 0, then I would start writing out the power series for it and get a naught plus a1 times z minus z naught plus etc. Let's go out to an minus 1 z minus z naught to the n minus 1. And the next one would be an z minus z naught to the n. And let's say that this one is f at 0. This one's f prime at 0 divided by 1 factorial. this one would be, let's say all these are 0. F n minus 1 derivative at 0 divided by n minus 1 factorial. Let's suppose they're all 0. So I'm supposing this is 0, this first derivative is 0, this n minus first derivative is 0. But let's assume this one's not 0. That would be the next derivative. Okay, so the function has a 0. As f of 0, it's a 0. But maybe it's got a higher order 0, which is going to mean that some of those derivatives vanish. Well, unless it's identically 0, there's going to be a first not 0 term. And so let's suppose that a capital N is not 0. Then, of course, what's left here is a series that starts at a n. Etc. And I can pull out that z minus z naught to the n. Then what's left with would be a power series that starts with a non-zero capital A sub n plus a sub n plus 1 z minus z naught to the 1 plus etc. And the moment when you realize that you know something is that power series there converges for exactly the same z that the power series for f converges. So let's call this thing capital F of z. And the aha I'm thinking here, the power series for f capital F of z converges for exactly the same z, because all I'm doing is pulling out a complex number. Z minus z naught is to the capital N is just a complex number. I factor it out. That doesn't change the convergence of that series. So the power series for the capital F converges for exactly the same z. As the series for my original function f. That means the radius of convergence of f is the same as the radius of convergence for little f. Okay? And so if I know that what I have is that f of z is equal to z minus z naught to the n times capital F of z. And let's let r be equal to the radius of convergence of little f. Then capital F is analytic on that same disk. And so this one's going to have the same radius of convergence. So F is analytic. It's kind of like a factored out of 0 on the disk of radius r. And something to note, notice that f at z naught is equal to an, which is not 0. And that's the fascinating thing to observe here. That shows you the zeros of analytic functions have to be isolated. Consequently, the 0 of little f at z naught must be isolated. meaning I can stick a disk in around there so that that's the only zero. There is a delta. Let's see, so delta would be 0 less than delta, probably less than or equal to r, probably less than r. Think of delta as small, such that z naught is the only zero of f in the disk of radius delta about z naught. That's what it means to be isolated. It's all by itself in there. And that's easy to see because we know that f is equal to a power series, so f is analytic, so f is continuous. So I guess I should say f analytic. I guess I'm using facts here. F equal power series is analytic because power series converge to analytic functions. So continuous. Its value there is, that's important to know, it's continuous. So, oops, what happened here? What? There it is. It's continuous. And its value is not 0 at z naught. So let's see if I know it's continuous. So here's 0. Here's my an, which is not 0. If I want to show that f is not 0, I want an epsilon in the definition of continuity that looks like this. So let's take epsilon less than the modulus of an. Then f of z minus an is less than that epsilon when z minus z naught is less than delta. I'm using the definition of continuity there. That would mean that f of z would be stuck in here somewhere. And so it couldn't be 0. So that's how you show that. Let's see, I'm running out of time. That turns, that's going to have important implications. It means the zeros of analytic functions can't pile up. And that's an important property. So the moral of next lecture's story is going to be zeros of analytic functions can't pile up. They can pile up at the boundary, but they can't pile up inside the omega. If they're going to pile up anywhere, they have to pile up on the boundary. That turns out to be a possibility. And that's going to lead us to start thinking about some topological properties. Any last minute questions about anything? I do that every semester. I forget I should prove that power series are uniquely determined before I try to do anything next. And every year I screw it up. Sorry about that. Maybe I'll change the order in my notes. Okay, that's enough for today.